Hello students, and welcome to a new lecture about the emission line spectrum. When atoms absorb energy, they must re-emit the energy as light of a specific wavelength. This was found in this very simple experiment. When we subjected certain atoms to high energy and found out what came, we filtered the outcome of that emission and made it go through a prism, and it was separated into what we call line spectrum. So this is a little bit different from a rainbow. The rainbow is continuous flow of color. This is here on the receiving board, you just find separated different lines, each one with a certain color. We call that the line emission spectrum, which is light emitted only at a specific wavelength, and it provides what we call a fingerprint for any given atom. So if I excite hydrogen, the light emission spectrum is different from the one that will come if I excite neon, or if I excite sodium, or if I excite copper, and so on. Let's look at this beautiful picture together now. This here is the emission line spectrum for different elements. So if you look here, the first one is for lithium, and the previous slide gave me the one for hydrogen, which is again shown here. And if you see, this is here the one for barium, and this one here is the one for neon, and so on. And it does act like a barcode. Every emission line spectrum for every single element is different and unique and acts as an identification tool for that specific element. So that led Bohr to have his first model of the atom. He said that the lines in those spectra correspond to energy of electrons quantized. So he is picturing the following. The nucleus is in the center where protons and neutrons are located. But then he is picturing that electrons are occupying certain energy levels, which are the circle around the nucleus. Each one of them has a different energy. N1 is one energy, N2 is a higher energy, N3 is a higher energy, and so on. The energy level allowed energy for any given electron. The innermost, as I said, the closest to the nucleus, are the lowest energy, and they are designated by quantum numbers that we call n. So every energy level has a quantum number. The first one is 1, which is the lowest energy. The second one is 2, and so on. The higher you climb up with n, the higher the energy. Now, to explain the line emission spectrum, if an electron is excited from level 2, let's say, to level 3, it has to come back after excitation. So you give it energy, so energy absorbed to go up in up level. So if energy here, let me write this down. If energy is absorbed, then electron go from lower n to higher n. But that's what we call excitement of the electrons. However, they have to come back, and when they come back, energy is emitted. And this is coming from higher n to lower n, and it is emitted in a form of a light. So this is the process that we call, this is here is excitation. Let's go back. This is here is excitation, and this is here is relaxation. So when the electron is in the relaxation, it comes down in energy, and that energy is emitted as a wavelength. That wavelength has a color. So this, if the electron is excited from N1 to N3, eventually it has to come down and when it comes down, this energy is emitted in a different color because every wavelength corresponds to different color. So now if we look at the energy emitted, this energy is calculated as we've seen before by multiplying Max Planck constant with the frequency or substituting frequency by c over wavelength. The ground state is the lowest energy state for any given electron, and the excited states, it's the new place that was promoted with a higher energy level when energy was absorbed. So now let's look at this picture. If you see here, this is a small amount of energy. So smaller energy correspond to longer wavelength and will correspond to the red line. Now high energy correspond to shorter wavelength, and that will correspond to the violet line, and this one in between will be the blue greenish one, and that explains the emission line spectrum. That explains why we have one line in the red, one line between blue and green, and one line in violet. Now, the problem with this model, that it was very simple because it only addressed the hydrogen atom. The hydrogen atom being the simplest atom, it only has one electron. So you can't get more simple than that. So what we learned at that point, that the quantum mechanics theory came in, and it did describe how electrons act as both particles and waves. We know that electrons do not travel in just circular orbits. We know that they occupy an orbital. An orbital is not a physical place, it's rather a probability map, which is a region of space that shows where electron is most likely be found. And it was described by the wave function. And the quantum mechanics definitely replaced the previous theory, because the problem with the previous theory, that it really, as I said, addressed only hydrogen, and it can only explain certain colors, but it wasn't able to explain the more complicated atoms with multi-electrons that has different colors that came from jumping between energy levels that were not clear in the hydrogen model. So what we also learn from the quantum mechanics, that we can never pinpoint the exact location of an electron. We can never say where the electron is or going to be found. We can only talk about the probability of where to be found. And again, remember, orbitals do not have definite boundaries. They are probability maps. This has now led Heisenberg to come with the uncertainty principle, that we cannot know both the momentum, which is mass times velocity, and position of a particle at any given time. We only know the electron density, which is the probability again of an electron where it can be found, and that was solved by the Schrödinger equation and function. So here is an example. The dot is the nucleus, and then there is a shaded area around it. The darker the shade, the highest the probability for that electron to be found. So that's an orbital. That shading, green shading around the nucleus, that's the shape of an orbital, which tells me where I can possibly find the electron. Where does it have the highest probability to be found? And the highest probability to be found, it looks like it is kind of a sphere around the nucleus. So that's the shape of the orbital in this case. So we will talk more about the different orbitals in the next lecture, and I will see you there.